All right, we'll get started today. So welcome back, everyone. And then, let's jump into lecture 2. So this is a lecture on system modeling, which corresponds to chapter 2 of the book. So I'll just note some of today might be review for some of you, some of it might be new. But I just really want to note that we're kind of cramming a lot of topics into one lecture here today. So this lecture and the lecture next Tuesday are going to be a little different, I guess, than the rest of the lectures, because we're going to talk about kind of those input components to the validation problem. So if you remember from last lecture, we had the inputs as a system, the system that we want to test, and then the property that we want that system to satisfy. So we're going to talk about kind of, in this lecture, how to set up the system, and in the next lecture, how to set up that property, and the rest of the course will be about validation algorithms. So I just kind of want to give a warning, today might be a lot, we might not actually get through all of it, we'll finish up what we don't get through next Tuesday. But if I am going too fast or I brush over something, definitely stop me and ask any questions that you have. The other good news is that this lecture is kind of self-contained, so everything we learn here, we're going to talk about how we can go about modeling the system, because we want you to understand various ways to do that when you need to set it up in the real world. But for the rest of the course after this, we'll actually just give you the system that we want you to validate. So everything, this lecture is kind of self-contained. Okay, but let's jump into system modeling. And I want to start again with just remembering the context we have here. So in this class, we're essentially finding out, as we said. And we said in the last lecture that, if we're here to find out, we don't really want to find out when it's too late. We don't want to find out when we've already deployed the system in the real world. What we'd rather do is find out in kind of this controlled, safe environment, unlike these people did. Okay, so like I said, we don't want to find out in the real world. What we do want to do is find out in simulation, because if things go wrong in simulation, it's not so bad, versus if things go wrong in the real world, we can get ourselves in a lot of trouble. So today we're going to discuss ways to model systems so that we can simulate them for offline validation. So by offline validation, I mean essentially not in the environment we're intending to deploy the system in some kind of simulated version of that. So plan for today, we'll start out with just some general thoughts I have on models that I want you all to know. And then we're just going to go through essentially the steps required for building models. So the first step is to select a model class. We'll talk about what that means. Once we have selected a model class, we typically have some set of parameters for that model class, and we need to figure out what they are. So that's the next step. And the final step is to validate the model. I'm not sure if we'll get to that today, but if we don't, we'll get to it on Tuesday. Okay, so let's start with some general thoughts on models. So there's many different types of models and simulators. I'm sure you've heard of many of them. And what's kind of interesting is they don't even necessarily have to be on the computer. So it's essentially just some kind of safe environment where we can find out without having to deploy it in its real environment. So an example of a model that's not on the computer would be like the neutral buoyancy lab at the Johnson Space Center. Maybe some of you have seen this before. Essentially, it's this giant swimming pool that astronauts can do their training in, which simulates what it would be like when they're doing a spacewalk on the space station. So this isn't actually a computational model, but this is a way for them to kind of find out what might go wrong in a safe environment, such as a swimming pool on Earth, not when they're out in the middle of outer space. So giant swimming pools are super cool, but in this class, we're going to focus on computational models. So mathematical models that we can simulate on the computer. So models vary in complexity. So for example, let's imagine that we're modeling the dynamics of an aircraft, so how an aircraft state evolves over time. And for example, one option here would be to just have a couple of equations that model its state. So this is just saying that our altitude at the next time step is our current altitude plus our vertical rate times some delta t, and similarly for the vertical rate. So this is just kind of two simple linear equations. Or what we could do if we want to model the dynamics of an aircraft is use this kind of very high fidelity flight simulator. So one flight simulator we use a lot in our lab is called X-Plane. And it has all these very complicated dynamics. So it's paying attention to the angles of the control surfaces on the aircraft. It's paying attention to the weight of the aircraft, the type of aircraft, the wind conditions, etc. So this is a much more complicated model. And there's kind of two ends of the spectrum. So we could have, just a very simple model like these equations here, or we could go all the way up to this very high fidelity flight simulator. And essentially the goal here is that we want to pick the model that is just complex enough to capture what matters. So if we don't have to, maybe some of you who've worked with X-Plane before could agree with me, you might want to avoid using this very high fidelity flight simulator in cases where it's not necessary. And we could just get away with kind of these simple equations. And knowing when we need something more complex versus less complex is typically problem dependent, but it's important when you're thinking about what model to use to try to understand the problem domain that you're in and pick something that's just complex enough. So a good way to summarize this is this quote from Albert Einstein that says, "Everything should be simple as possible, but not simpler." Maybe. We're not really sure if Albert Einstein said this. We wanted to put it in the book, and Mykel's requirement was if we put it in the book, we need to have a citation for it, and so I started searching all over the place, and everyone's kind of like, all the sources online are like, he probably said it, but they're not really sure. He said something similar to it, and so then everyone's like, oh, well, that's probably what he meant. So either way, it's a good motto to live by when you're selecting your models. And then we didn't put it in the book for that reason. Okay, another kind of thing that can vary with models is whether they're white box or black box. So a white box model means that we give it some inputs. So in this case, we'd give it, for example, the current altitude of the aircraft and its current vertical rate. And then we can see what equations are involved in determining the outputs. So the next altitude and the next vertical rate. A black box model, on the other hand, essentially what we're doing here is we give it some inputs, and then we don't really get to see what happens when it's doing things to these inputs. We just get to see what the outputs are. And then, of course, we can have something in the middle where maybe we know what's happening to some of the inputs. So in X-Plane, for example, we know some of the dynamics equations that it's using, but maybe we don't know exactly what's going on inside. Okay, so with that, there's kind of a few key challenges that we have when we create models. The first one is that, kind of like we were saying, the model needs to be expressive enough to capture all possible scenarios the system may encounter, but you don't want it to be too expressive. So I want to kind of actually dwell on this point, this challenge, for just a little bit longer, because I think it's really key and it's really important. Because when you think about really what this means to capture all possible scenarios, that's like a pretty tall task. So imagine, for example, that our system is a self-driving car. So now all possible scenarios is like all the pedestrians it might see, all the other cars on the road, what they might do, bikers, construction, it's so many things. And so this is definitely like, no easy feat here, and it's worth putting a lot of effort into making sure that you capture all of these scenarios. Another thing I'll say is I've given a number of talks on validation at this point, and at almost every single talk, I get one question that is this, which is, how can I capture all possible scenarios my insert crazy complex system here will end up in? And they'll say, like, I don't even know what they are. So like we were just saying for the self-driving car, like, how am I supposed to figure out all possible scenarios that this car is going to end up in? And my answer to them is always, yeah, it's a problem. This is extremely difficult to do, as I was saying. But I think there is some hope here, or kind of a silver lining, which is stay tuned for the runtime monitoring chapter, because I think what we could do is we can make the best effort to capture all possible scenarios or things that might occur in our model. But we also could realize that we are probably going to miss stuff, especially for very complicated systems that operate in very complicated environments. So what kind of the next best thing we could do is deploy these systems with runtime monitors so that when we're operating at runtime, we can try to understand if we're in a scenario that we didn't model or something that we are unfamiliar with. So that would be my answer, but it is really a challenge. Okay, second challenge is, we're going to talk a little bit about this today. We have to base the model on something. We need to know something about the real world, and we could either get that from data or expert knowledge. But both of those can be kind of difficult to obtain. For data, you might need to then go into the real world and collect this data, or you need to find an expert or be an expert yourself. And then finally, once we kind of have this data or knowledge, we need to actually create the model. And one way we often do this is by optimizing for some objective, which we'll talk about today. Okay, another quote. All models are wrong, but some are useful. Maybe you guys have seen this before. The idea here is just that all of the models that we make, they're never going to perfectly model the real world, but if they model it well enough, they'll be useful to us, and our validation results that we use the models to get will be useful to us to make decisions. So that was said by British statistician George Box, for real. We actually found a citation for the book for that one, so we put it in there. Okay, let's do some math then. So the first thing we're going to talk about, the first step in creating a model, is to select a model class. So in this class, we're going to focus on probabilistic models, and we'll talk exactly what it means to have a model class that's a probabilistic model in a second. First, I want to think about what exactly probability is. So there's lots of different ideas out there of how to kind of describe probability. Here's one of the most interesting ones that I found recently. It basically says why probability probably doesn't exist, but it's useful to act like it does. And just in case you can't read this kind of smaller text below it, it's quite interesting. It says, all of statistics and much of science depends on probability, an astonishing achievement considering no one's really sure what it is. So I found this kind of interesting. If anyone's interested, you can check out this article. It's quite philosophical about the world and randomness and outcomes. We're not going to be so philosophical in this class. We're going to give it an actual definition. But we're just going to say the probability of a particular outcome is a number between 0 and 1 that quantifies the likelihood of that outcome occurring relative to all other possible outcomes. Okay, and so the way that we often describe probability is using probability distributions. And so this is typically what we mean by a model class, is we'll say that any different types of probability distributions are essentially different model classes. And a probability distribution is a function that assigns probabilities to different outcomes. So in this class, we'll talk about two different types of probability distributions. We have discrete distributions, which operate over variables or events that have a discrete number of outcomes. So for example, here's an example of a discrete distribution with 6 possible outcomes. So you could think of this as like rolling a dice. Then we have continuous distributions, which are defined over variables that have a continuous set of possible outcomes. So you could think of this as maybe a variable that represents the height of a student if we just randomly selected them from this class. We typically define these distributions using something called a probability mass function for a discrete distribution and a probability density function for a continuous distribution. In this class, we're going to represent probability mass functions with a capital P and a probability density function with a lowercase p. And the way that these work, they have slightly different properties. A probability mass function, the values need to be between 0 and 1. For a probability density function, the values need to be just greater than or equal to 0. It just needs to be positive. For a probability mass function, the sum of all possible events, the probability of all possible events occurring, must add up to 1. And then kind of the equivalent for continuous distributions is that the integral of all possible values of the variable, so from minus infinity to infinity, needs to integrate to 1. And the idea here is that for a probability mass function, it outputs actual probabilities. So if we input a value saying like, x equals 4, so we're saying what is the probability that x equals 4, the output of this p of x will be that probability. So that's what this plot is showing here, so you can see it's around like 0.25. Over here, we have, when we look at probability density functions, the value that you get out is not an actual probability. So if we input this value a into p of x, we don't get the probability that a occurs. In fact, the probability of one single value is actually 0, which is kind of strange to think about. And typically for these types of distributions, we think about what is the probability of the variable lying in some continuous range. So what is the probability that x is between the value a and b? And in order to find that, we just integrate the probability density function in that region. So it corresponds to the area under the curve. Okay. Hopefully this might be review somewhat. So we often represent these probability distributions using a set of parameters, which we'll call theta. So for discrete distributions, the parameters look like this, where this is essentially one way to represent the parameters, where we have, for example, for x equal 1, the probability that x equals 1 is theta 1. The probability that x equals 2 is theta 2. 3 is theta 3, and so on. And so we just have one parameter for each possible outcome, saying the probability of these outcomes. For a continuous distribution, this is an example of a continuous distribution called a normal distribution or a Gaussian distribution. And they often have parameters as well. For a Gaussian distribution, the parameters we often use are its mean, which we'll represent using mu, or its standard deviation, which we'll represent using the letter sigma. So the theta, the set of parameters for a Gaussian distribution, is that mean and standard deviation. So now we need to decide how we decide on a model class for our whatever problem we're trying to solve or whatever system we're trying to model. And the key consideration here is that we need a model class that's expressive enough. So what do I mean by expressive enough? There needs to be some setting of the model parameters for which the model will fit the data well. So I'm going to go through a Pluto notebook now to kind of describe this idea. So we're going to start here with a Gaussian distribution. And we're going to say that the blue points there, so everything, that kind of blue histogram, is plotting a bunch of samples we have. So maybe this is a bunch of sensor measurements we got from our system. Essentially, this is the data that we're trying to match. And then the sort of magenta or pink line there is showing the distribution that we currently have. So we basically want to line up that pink line with our data, and then we can say that we've done a good job modeling it. And we have these kind of parameters to play around with for our distribution. For a Gaussian distribution, the parameters we can play around with are the mean and the standard deviation. So I'll kind of mess with the mean here and do my best to kind of get this distribution lined up. And then we can, control its width using the standard deviation. And yeah, given my fine finger movements, this is about as good as I can do. So you can see, though, that this matches up pretty well. We're able to get a distribution that lines up pretty well with the blue. And so this is a good fit. So I would say in this case, a Gaussian distribution is expressive enough to fit our system and to kind of accurately model it. But now let's imagine that we sample a different system and we get a data set that looks like this. So now in this case, we can mess around with the mean a little bit, see how well we can do. But, kind of no matter what we do here, we're not really ever going to get something that fits this distribution well. And the reason for that is because this distribution here is multimodal. So it has kind of two peaks in it there. You can see there's one on the right, one on the left. And a Gaussian distribution is unimodal. So no matter what we do to mu and sigma, we're never going to get a distribution that has that shape. And essentially what that means is that a Gaussian distribution is not expressive enough to describe this data set. So there's a few things that we can do if we find that we have a data set that's not kind of modeled well by these simple distributions. There's a few different ways that we can increase the complexity of our model class. One option is to create a mixture of simpler distributions. So for example, right here, I'm showing what we call a Gaussian mixture, where we take two simpler distributions. So in this case, we take two different Gaussian distributions. We can take more than two, but for this example, we're just showing two. And then we apply a set of weights to them to kind of balance between the relative weighting of each of those distributions. So now we have 5 different parameters that we can try to tune. And we'll see if we can find basically a setting of these parameters that allows us to fit this data set well. So I'll try that real quick. I'll be honest, I have the answer, so I'm just going for it here, right to the answer. But it might be kind of difficult to pick these parameters at some point. Okay, so essentially I'm messing with kind of the mean and standard deviation of each of them. And then we can mess with the relative weighting of each of them. So this is getting further from what we want. But you can see kind of how the shape of the distribution changes as we mess with this relative weighting until we get something that fits pretty well. What questions do you have on this? Yeah.
I'm just realizing there's a formula there now. Is it just to balance between like the two Gaussian?
Yeah, that's exactly right. And the weights need to sum up to 1. And the reason for that is we still need to have a valid probability distribution, so it still needs to integrate to 1. Question? Yeah.
So what I'm understanding is that we have this like data, and then we are trying to like figure probability distribution. So are you like right now saying that the model is the probability distribution?
Yeah, exactly. The model is a probability distribution. So in this class, all of our models, for the most part, are going to be probability distributions. And I was just remembering I'm supposed to repeat the questions for people that are watching online. The question was, what is this kind of pink model? And what is this pink probability distribution? Is that the model, the thing that we're trying to come up with? Yes, that is what we're trying to do in this lecture. And the other question was, what do the weights mean between the two distributions that make up the mixture? Yeah.
Is there a particular reason we're mixing? Obviously, it's simple in this case. The same distribution, like, is it possible to mix multiple different types of distributions in one mixture?
I don't see any reason why you couldn't, as long as you make sure that it integrates to 1. But yeah, you can do that. Any other questions? Oh, sorry. The question was, could we mix different types of distributions in the mixture model? Okay. So that's one way that we could make more complex distributions, and you can imagine as we add more and more Gaussians or use different types of distributions, that increases the amount of data sets we would be able to fit. Another way to make more complex distributions is to transform a simple distribution. So let's imagine that we have some simple distribution, we'll say just kind of a Gaussian distribution with a mean of 0 and a variance of 1. And then let's imagine we're now going to draw 10,000 samples from this distribution. So what that line of code at the bottom there is doing is just saying we're going to take 10,000 samples from this normal distribution. We're going to call that those samples z and store them in a vector called z's. And now, okay, so here's what they look like. The normal distribution is that pink line there, and you can see since we just drew samples directly from it, the samples fit that normal distribution. Now, let's imagine that we take all of these samples and we apply some function to them to get some new variable that we're going to call x. So in this case, we're going to apply the cube root function. So we'll define this function as f of z and say that that's equal to the cube root of z. And then we'll just apply that function to all of the samples that we just took. So now we took all those samples from the normal distribution, took their cubed root, and we stored them in this vector called x's. So then we can plot a histogram over the results here. And this might look kind of interesting to you. So what just happened is we took all of the samples that came from that blue histogram, we just applied a function to them, and then we got this purple histogram, which is much more interesting looking. It's now bimodal. So we've kind of done what we wanted to in creating a more complex probability distribution. But what we need to know, or what we might want to know, is what is the probability density then of this new distribution? So how do we get this pink line that we had for the other distribution? So let's just kind of make sure we define some notation here. So we're going to say the variable we took from the simple distribution, we call it z. It comes from the distribution that we're going to call p sub z. And then we transformed it to this variable we called x, and we want to know what is p sub x. So what is the formula for p sub x? And x is equal to f of z. So it turns out that if f is both invertible and differentiable, then we can actually calculate the density of the resulting random variable. And it follows that formula there, which essentially involves the inverse of f. So that g you see in the formula is the inverse of f. So again, we need that function to be both invertible and differentiable to do this. Luckily, cube root is both invertible and differentiable, so we can test this out. So we can say g of x is equal to x cubed, so inverse of cube root is equal to x cubed. The derivative of the inverse g prime of x is equal to 3x squared. So we've got that implemented, and then we can just implement what's shown in that equation there. So we say that our new density p sub x, yeah.
Can you zoom in?
Oh yeah, of course.
Thank you so much.
Is that better?
Yes.
Okay. So our new density now is p sub x, which is the PDF, so p sub z, of g of x, so that's the PDF of a normal distribution, because we remember z was distributed according to a normal distribution. Then we input g of x, and we multiply it by the absolute value of the derivative of the inverse. So it kind of seems like a lot's going on here, but if you just kind of break down what each of these things are representing and look at this formula, you can calculate this new density. So once we use that equation, you can see we get the density of the transformed distribution, which lines up well with our histogram of those samples from it. What questions do you have on that? Yeah?
Why did you sample the original distribution?
Why did I take samples from this distribution?
Yeah, like why did you, I'm guessing that that distribution has some sort of data already, like in the first place. Was there a reason for drawing all these again?
Okay, great question. So I think, let me try to make the connection between what we're doing here and what we would do if we were trying to make a model in the real world. So in the real world, let's say that we sampled something and we got this purple data. And we're like, okay, we need to fit a distribution to this. We need to pick some sort of model class. Well, how are we gonna do that? We need something that's bimodal. And so one thing we could do is maybe we could try a Gaussian mixture. Now I'm showing you one other thing we could do. We could say, okay, how do we define this? Maybe let's start with a distribution we know we know a lot of things about, so that's like where we get this normal distribution from, and then let's transform it in some way to try to make it fit this data. Does that answer your question?
I think so. So it's not that you already have data, like you essentially try to manipulate like the Gaussian in this case based on that you know that you can make it become a multimodal.
Yeah, that's exactly right. So this would be the data that we're given. We want to fit this data, but we don't have any nice distributions we can use to fit this data. So one thing we could do is we could try to create a mixture of distributions, or we could say, we know how to define this distribution, so let's define our model as a transformation of that simpler distribution. Yeah.
So, further clarification. So is that just the transformation that we're making on this, and how did we find that?
Great question. I just picked it because I knew that this one makes it look cool. It won't always look this cool depending on the F you pick. And again, we needed it to be both invertible and differentiable. But this actually leads me very well to my next point. So the question was, how do you pick F? So what's really cool is I just picked this nice F that allowed us to transform this unimodal distribution into a multimodal one. And this type of transformation can be quite powerful. And if you've heard the term normalizing flows before, this is kind of the key idea behind normalizing flows. So normalizing flows use a series of parameterized, differentiable, and invertible functions. So in normalizing flows, essentially what they're doing is trying to learn that transformation. So I just picked cube root because it works well, but we don't always know what works well if we're trying to transform to some very complicated distribution. And so what normalizing flows do is kind of let there be a set of parameters for these invertible transformations, and they learn them so that we can transform simple distributions to complex ones. So there's a nice tutorial I linked in this notebook. I can also link it on Ed if people are interested. You can learn more about it. The normalizing flows are outside the scope of this class, unfortunately, but what I really just want you to know is kind of this simple change of variables formula, assuming that I gave you a transformation. But just to get you excited about them, here's a super cool animation of transforming a very simple distribution into something more complex using this idea of a normalizing flow. What other questions do you have on this?
because of the optimization process that's going on to find these which functions to use? Or I see this animation, but what is that over?
Yeah, the question is why is it called a flow? To be honest, I don't know for sure. I think it's because you have this kind of series of transformations, so it's kind of like it's flowing through that. I don't know. Does anyone have any other? Yeah, okay. Okay. So yeah, like I said, we needed this kind of transformation we applied to be both differentiable and invertible. We could still do what we just did without having a differentiable and invertible transformation. We just won't be able to calculate the density. So we could still draw samples though. So for example, we could take a bunch of samples from a uniform distribution, which is what's shown on the left in blue, draw samples, and then maybe pass them through some crazier function like x of z times sine of 8z, and then we get the samples that are shown on the right. So we have this very interesting looking distribution. Unfortunately, we can't calculate the density of it, but sometimes that's okay. Sometimes we only need samples from our distribution, so we could just get the samples. So let's go back here and review what we just talked about. So what we showed was basically if a simple distribution doesn't fit the data that we gathered from the real world well, then we need something more complex to model our data. One way to create a more complex model was to create a weighted mixture of simple distributions. Another way to make that more complex model was to apply a functional transformation to a simple distribution. So in this case, we took our distribution P of z, which was a Gaussian distribution, we applied the cube root function, and we got a bimodal distribution. This is the formula that we used for that. And as a note that I've said a few times now, this formula requires that f is both differentiable and invertible. But even if it's not, we could still apply some sort of functional transformation. We're just not going to be able to calculate the probability density function, but we could still draw samples from it. So these, for example, would be samples from a pseudo-random number generator, something that we can sample using any sort of programming language. For example, in Julia, you can just call rand and you'll get these types of samples. And then we can transform them using some more complicated function. So at the risk of using lots of buzzwords, we typically call models represented in this way generative models. I'll just use some more buzzwords anyway. So you've probably heard of generative adversarial networks, variational autoencoders, maybe you've heard of diffusion models. These models all kind of work in this way. So they take samples from a distribution we know how to sample from, and they transform them in some way to some more complicated distribution that models something that we care about. So for example, maybe they take a bunch of samples from a multivariate normal distribution, they transform them some way, typically the transformation involves a neural network, and then you get some interesting set of samples like images of cat faces. All right, back here. So everything we just talked about for now was just talking about if we have one variable, so only one event that we care about the outcome of. So maybe this is like a sensor that's observing the altitude of the aircraft, and we just have one observation, which is the observation of the predicted altitude of the aircraft. And we're trying to model that sensor. We also might have multiple variables involved. So maybe we have a sensor that's predicting both the altitude and the airspeed. And in this case, we're typically interested in joint or conditional distributions. So a joint distribution is just a probability distribution over multiple variables or multiple outcomes. Sometimes we also call this a multivariate distribution. And it represents the likelihood of multiple different outcomes occurring simultaneously. So for discrete distributions, we still represent them using probability mass functions, but now we have two inputs to them or more. So we have, for example, the probability of x and y occurring. We can represent them using tables. This is a very common representation that we'll use in the class. Essentially, the way to read this table is by saying, assume here that x and y are both binary, so they have two possible outcomes. X could either be 0 or 1, and y could either be 0 or 1. And what this table is showing is if x is the probability that both x is 0 and y is 0 is equal to 0.1. The probability that x is 0 and y is 1 is 0.2, and so on. And this is a valid probability distribution. So that means that the entries in this table need to sum up to 1. We also have continuous joint distributions. So in this case, we now have a probability density function over these variables. One very common continuous probability distribution for multiple variables is a multivariate Gaussian distribution. So we're extending the Gaussian distribution to multiple dimensions. It's defined by a mean vector, which kind of specifies the center of the distribution, and a covariance matrix. And I don't know if it's just me, but like covariance matrices like scared me for the longest time. So I just want to go through it real quick. What exactly the entries mean, because there's really nothing super crazy going on here. So here's a multivariate Gaussian distribution. So its mean is kind of in the center of that circle there. This is a plot of the contours of the probability density. So brighter blue colors will indicate higher density. And so here's the current covariance matrix we have. So let me kind of go through each entry. So the upper left entry there is kind of showing you how much does x vary with itself. So how much does the variable on the x-axis vary with itself. So you can see if I increase this value, then we get, kind of a wider spread along the x direction. And if I decrease this value, we get kind of a narrower spread. Okay, but nothing really happened to y at all. Similarly, the value on the bottom right of this covariance matrix tells us how much does y vary with itself. So it's a very similar story. If we increase this value, we increase the spread of y. If we decrease this value, we decrease the spread of y. Let's put that back. Okay, and then the off-diagonal ones, which I think is what tends to confuse people sometimes, is just how much do the variables vary with each other. So right now it's set to 0, so you can see there's not really any correlation between the values of the variables, we just get circles there. But now let's say I increase it, so that means that x and y vary positively with each other. So now we can see that if we have a positive value of x, it's also more likely that we're going to have a positive value of y. And similarly, if we have a negative value of x, it's more likely we're going to have a negative value of y. So it's kind of like these variables have some correlation between each other. And the higher this value is, the more correlation we have. So the more strongly we see that trend. And then similarly, if we go the other way, it's just saying they have the opposite correlation. So if we have a positive value of x, we're now more likely to have a negative value of y. Okay, so that's a multivariate Gaussian distribution. Hopefully there's no more fears of covariance. All right, so one more note here. If two variables are what we consider independent, then their joint distribution is just the product of their individual probabilities. Otherwise, this is not necessarily true. So I just thought I would do a fun little aside here. So we've been talking about wisdom teeth. And it turns out we have this very weird combination of wisdom teeth among the 4 textbook authors. So like I said, so I never had any. Anthony, who's our other author, he also never had any. Robert has all 4, and Mykel had 5. So we thought maybe it would be fun to just calculate the probability that this happens. So let's just do that real quick. All right, let me see here. Can I edit this? Okay. So essentially what we want to calculate here is the probability that I have 0 wisdom teeth, so that's S0 for Sydney. Anthony also has 0 wisdom teeth. Robert has 4 wisdom teeth, and Mykel has 5. And because we're going to assume these are all independent events, so the number of wisdom teeth I had, I don't think really affected the number of wisdom teeth Anthony had. And so we're just going to say then that's the probability that I have 0 wisdom teeth times the probability that Anthony has 0 wisdom teeth times the probability that Robert has 4 times the probability that Mykel has 5. Okay, and then if you assign numbers to all of these probabilities, you get something like 0.00017. But I'll point out these are sketchy numbers from Googling /ChatGPT. So take that as you will. But there you go. So very unlikely combination of wisdom teeth for the textbook authors. And then just in case you really want to explore this topic further, I'm not going to go through this in class right now, but I actually took the time to figure out what is the probability that the sum of the number of wisdom teeth of the 4 textbook authors is equal to 9, because that feels like a really weird number. So if you want to know, that probability I got to be around 3%, and I actually plotted the full distribution over sums of wisdom teeth for 4 book authors, all based on the sketchy assumptions from Google and ChatGPT, so take that as you will. But it is kind of interesting. You can see there's like peaks at 16 and 12. So most likely, 3 had 4 and 1 had 0, or everyone had 4. Yeah, kind of interesting. Okay, now we'll move on to conditional distributions. So this is a distribution over a single variable or a set of variables given the values of one or more other variables. So this is saying here, in this case, we're saying we know the value of x. What does that tell us about the probability of the outcome y? And we can define that in terms of the joint probability and the univariate probability, saying that this is equal to the probability of y and x occurring divided by the probability of x occurring. So in the discrete case, again, we have this kind of probability mass. We can use a table to represent it. So what this is showing is essentially the probability that if x is equal to 0, what is the probability that y is equal to 0? And for this row, it says, given that x is equal to 1, what is the probability that y is equal to 0? There's 2 entries in this table missing. Can anyone tell me what this first entry should be? 0.9, yeah. So if x is 0, the probability that y is 0, I guess I should say this was a binary variable. I wasn't trying to trick you here. So if x is 0, and we know the probability of y is 0 being 0 is 0.1, the only other option is y being 1, and so it must be the case then that has a 0.9 probability of occurring, because we need our probabilities to sum up to 1. Similarly here, if x is equal to 1, we know the probability that y is 0 is 0.5. The other option is that y is equal to 1, and so the probability missing here is 0.5. For continuous distributions, we can also have conditional probabilities. Here's a really common one that we're going to use in this class, where we have a conditional Gaussian distribution. So what's going on here is we have a normal distribution, so y is distributed according to a normal distribution. But that distribution, the parameters of that normal distribution depend on x, so it's conditioned on the value of x. In this case, we're saying it's just the mean that depends on x. The mean is actually just equal to x. So you get something like this, where over here, on the x-axis, we say the mean is equal to x, so for this value here, we kind of have a distribution that looks like that. For this value here, it has a mean here, so we have a distribution that looks like that. And if you plot all of those together, with the brighter colors indicating higher likelihood, this is kind of what that distribution looks like. Okay, so yeah, one note here, we're going to be talking about conditional distributions quite a bit, because if you remember from the last lecture, the distributions that we want to model for our system are all conditional distributions. So for the agent, for example, we want to know the probability of an action given an observation. The transition, we want the probability of the next state given the current state in action. And for the sensor, we want the probability of an observation given the current state. Okay, what questions do you have on model classes before we move on? Oh, yeah.
How to read the continuous distribution graph?
Yeah, absolutely. Go back here. So the question was if I could explain this continuous distribution graph again. So the brighter colors indicate higher probability, and we're saying that the distribution over y is dependent on x. So when x is at this bottom corner here, the mean of the distribution over y is just equal to x. So mu is equal to x. So the distribution over y is going to look something like that. And so that's why we see kind of bright colors here centered around the mean, and then these darker colors out here. Now if x is over here, the mean is still going to be equal to x, so the mean of y is going to be right here, and then we're going to have a distribution that looks something like this, and you can kind of see that kind of smoothly changing as we change x.
diagonal kind of view.
Yeah, exactly. And that's only because we said that the mean is going to be equal to x. So it kind of, the highest likelihood thing is going to be y equals x, and then it's going to kind of spread out from there. Yeah, no problem. Let's go on to parametering. So now we've picked a model class, and you saw we did a lot of messing around with parameters here. How do we actually decide what parameters we want for our model class? So what we want to do here is we basically want to automatically do what we were doing in that notebook. So dragging around those sliders was not so easy. And you can imagine, what if we have like millions of parameters, like neural networks have millions of parameters. How could we, we're not going to sit there dragging around sliders all the time. So to kind of formalize what's going on here is we had some set of parameters theta, and we had some data set that we observed from the real world that we want to model. And we want to find the parameters theta that best fit this data set. So how do we know which of these parameters are best? One option is to look for the ones that make the data most likely. So given a set of parameters, we can calculate the probability of observing the data set we did. So we could say, let's assume the parameters were this. What is the probability then that we got that data set? And the higher that probability is, the better it is. And basically what we want to do is find the parameters that make the data seem the most likely to have occurred. So the way that we write this is saying theta hat, so our estimate for those parameters, is equal to the theta that maximizes this probability. And what this says is this is the probability of the data, so D is the data set, so all those data points that we observed, all those blue data points that I was showing, given theta, given the parameters. We're going to assume that our data set is some set of observations from the world, so maybe this was a bunch of sensor measurements we got. And then another way that we're going to write this, so we use this notation sometimes in the book, it's the colon notation. So whenever you see this kind of 1:m, it just means observation 1 through observation m. Okay, so we're going to make an assumption here, which is that all the data points that we gathered were independent and identically distributed. And what that allows us to do is use what I was showing you before, where we could take those independent events and just multiply their probabilities. So then the probability that we got this whole data set, given our parameters, is just the probability that we got the first observation given our parameters times the probability that we got the second observation given our parameters, and so on, all the way to the probability that we got the nth observation given our parameters. So we can concisely write that as this product from I equals 1 to m of all of our probabilities of the observations given some set or some choice for the parameters. One thing we're going to do that might seem a little weird at first is take the logarithm of this. The point of that is just it typically results in better numerical stability. Nothing crazy going on. But when we take the log, we end up changing this product into a sum, which makes things a little bit nicer. And then it turns out that maximizing the log will have the exact same solution as maximizing it without the log. And so we can rewrite our maximization problem that we're trying to solve like this. So we're saying the theta we choose is the theta that maximizes the sum of the log probabilities of all of the observations given our choice for theta. Okay, so to summarize what we just did here, this is something called maximum likelihood parameter estimation. So we started by saying we just want to take the parameter that makes the data we observed most likely. We assumed independent observations, which changed it into this product, and then we took the log just to make the optimization easier, and we got this summation of log probabilities. Okay, so let me just show you really quick a very silly way to solve this optimization problem. So one thing that we could do here, let's say, for example, that we have this data set here of x and y values. So I didn't label the axes here, but the x-axis says like some input x, and then maybe this is, for example, the state that our aircraft was actually in, and then the y value is some observation. And so maybe this is like the observation, for example. And what we want to do is fit a conditional probability model to this data. And we're going to say, probably should have written what it is, but we're going to say the model looks something like this, where we have these kind of parameters here, where we're going to say it's a normal distribution. centered with a mean that's some linear function of our input x and some standard deviation. So this we're going to call theta 1. It's already filled in here, but we'll just call it theta 1, which is what we're trying to find. This is theta 2, what we're adding on, and then this is the standard deviation. So one kind of silly way to do this optimization is to just mess with these parameters until we get the lowest possible likelihood. So for example, I can mess with theta 1, which is kind of the slope of that linear function that determines the mean. So that's why it's kind of changing the slope of this probability density here. So I could just mess with that for a while and watch the log likelihood that comes out and try to find, some setting of these parameters that gives us the best log likelihood. So for example, I'm noticing that log likelihood gets higher as I decrease this variance. So maybe I'll keep decreasing it until I get, some log likelihood that's no longer increasing. So it decreased, so now I'll go back up. And we could just do this for a while. Okay, so we had our objective to optimize, but again, we're still using these sliders, so that's why it's kind of a very silly way to do this optimization. It turns out there's a much better way to do this optimization, which is to actually just give it to an optimization algorithm that can do this for you. So we're not really going to talk about how these optimization algorithms work. We'll talk a little bit more about them later in the quarter. But for now, I just want you to think of them as kind of these black boxes that take in some objective and the parameters that they're allowed to change, and then they give you back the optimal parameters. Okay, more buzzwords. There's gradient descent. You may have heard of atom, genetic algorithms, momentum. There's lots of different types of optimization algorithms. And we'll talk a little bit more about them in chapter 4. But if you really want the full story on these, you should take AA222 next quarter if you haven't taken it already. Questions on this? Yep.
So this might be stepping outside the scope of the class a little bit, but if we have, say, a data set and we have a probability distribution that we want to transform in order to represent the data points, would it be possible to use a functional to find a function with which we can transform the probability distribution? Yeah. So the question was, if we have a data set and we have some simple distribution we want to transform in order to get that data set, can we try to learn that function? Is that correct? Can we try to learn that function? Yes, exactly. So that's actually exactly what normalizing flows do. That's kind of what generative adversarial networks do. They're basically learning this transformation of a simple distribution to a much more complex distribution. But yeah, I think models of that size are outside the scope of this class. All right, so here's another code snippet. So this is one of the algorithms from the book. We call it maximum likelihood parameter estimation. It takes in this likelihood model, which is a function that given some input x and some set of parameters, it gives us the probability distribution over y. And then we have some optimization algorithm or optimizer. There's various tools in Julia you can use that kind of have off-the-shelf optimization algorithms. You don't need to worry too much about how to implement those. And then we have this function that we call fit that takes in our algorithm and some set of data. We set our objective to be the sum of the negative log likelihood of all the data. The reason that it's negative is because oftentimes our optimizers minimize, they don't maximize. So we want to maximize the log likelihood, which means we want to minimize the negative log likelihood. But all this is doing is calculating the likelihood of each of our data points given some value of theta, the value of theta that gets input to our objective, summing all of these log probabilities. We give this as the objective function to the optimizer, and we say, find us the best theta for this particular objective. And that allows us to pick these parameters. So let me show you what this looks like. So here's essentially implementing this for the problem we were looking at before to find that theta 1, theta 2, and theta 3. So we're saying here that the likelihood is a normal distribution where we take our theta 1, we multiply it by the input x, we add on theta 2, so this is just a linear function of x, and then theta 3 describes the standard deviation. You don't need to worry too much about this exponential here. It's just to make sure that we always get positive values for the standard deviation, but you can kind of ignore that just for your understanding. Then we define this optimizer. We're using a Julia package called Optim, which implements lots of different optimizers. The specific optimizer we'll use is gradient descent. Again, you don't need to worry too much about the syntax here, but essentially what's going on is we're just defining this likelihood function for our model class, and then we're picking an optimizer. We then feed this to our algorithm, so we create an algorithm with that likelihood function and optimizer. We call fit, and then I'm printing out the results. So if you see here what's going on is what we ended up printing out is we said the best model was 0.999x plus 0 and a variance of 0.05 squared. And if we go back and look at these values that we found by just kind of hand tuning everything ourselves, we got something very similar. So we got 1 for theta 1, 0 for theta 2, and 0.05 for theta 3. So what this did was just kind of automatically do that process for us. And you can see it gets that log likelihood, and that's what the plot looks like with respect to our data. Okay, so this optimization problem leads to many common loss functions, actually. So buckle up, because I'm about to show you my favorite derivation ever. Okay, so here's how it works. So let's say that we want to find the parameters theta for a conditional Gaussian with constant variance and oh, that's it. Okay, with constant variance. So we're going to say we have this model that is going to be P, yi given xi, so this is our data point, is equal to a normal distribution with over yi, where our mean is some function of xi, and our variance is some constant value. And we're going to assume we have this data set of a bunch of xy pairs. We have x1, y1, x2, y2, and so on, all the way to xm, ym. And then we want to find the maximum likelihood estimate for this type of model class. So we'll say theta hat is equal to the argmax of theta of the sum over all of our different data points of the log probability of them. So that's just coming from the equation that's up here. And then we'll say we just defined that probability to be a normal distribution, a conditional Gaussian. So that's going to be the log. We're just going to plug in for this now. So it'll be the log of this normal distribution, which has a mean as some function of x, and a variance sigma squared. So now I'm just going to plug in the equation for a normal distribution. So that allows us to say we have argmax theta log. So this is just going to be the equation for a normal distribution. So it's 1 over root 2 pi sigma squared times the exponential of negative y I minus f theta xi squared over 2 sigma squared. Okay, gonna come up over here now. Okay, so then I'm just gonna now take the log of this formula to simplify a few things. So that's gonna be the log of this times the log of this. So we're gonna get argmax theta log 1 over root 2 pi sigma squared minus, so when I take the log of the exponent, it just cancels those two out. So I just get minus yi minus f theta xi squared divided by 2 sigma squared. And now we'll think about what we're doing here. So we're solving this maximization problem over theta. So anything that doesn't have a theta in it, we don't actually really care about because it's not going to affect the value of this objective. So we can basically just cross out this whole term because it has no theta in it. And we also don't really care about this denominator because it also doesn't involve theta. So then we can rewrite this with those things gone. And we'll get sum I equals 1 to m of negative yi minus f theta xi squared. And it turns out the argmax of the negative of this function is going to be the same as the argmin of the inverse, or the converse of that. So we'll say this is actually the argmin of theta of the sum from I equals 1 to m, yi minus f theta xi squared. Okay, so maybe this looks familiar to some of you. If it doesn't, I'll just tell you what it is right now. This is just the least squares objective. Pretty cool. So I, just naively was applying least squares my whole life until I saw this. And it turns out when you're applying least squares, what you're doing is you're actually assuming that the data comes from a conditional Gaussian model where your inputs, so your x's, essentially determine your y's by passing them through some function and adding some Gaussian noise with constant variance to it. Kind of blew my mind when I saw this. Any questions on this? Yeah. Yeah, actually, you know what? I anticipated this getting messy, so I copied the one from the book. So here's a much cleaner version of this. But I will post this with my annotations later. Any other questions? Yeah.
How this blew your mind, like the part about like what specific things that it was building upon, like the different assumptions that we're making. I just want to make sure.
Yeah, sure. So let's say that we have a whole bunch of data points, and they're XY pairs, so we have some input-output pairs, basically. And what we want to do is come up with a model that predicts Y given our input X. And so what we're going to assume is that to generate that data, so we don't actually know how that data was generated, it was just given to us, but we're going to assume that that data was generated by taking X, applying some function to it, parameterized by some values theta, and then adding some noise to it because the world is kind of just noisy or something, or we're missing something in our function. And that's how we got the Y value. And then what we're trying to do is, it turns out that if we do this least squares objective, that's the assumption that we're making. We're assuming that the data was generated in that way. Yeah.
And so is the dual also true that if we don't know something about the trust structure of the data, we should not be using MLE? Because it's like bad to assume the Gaussian property when it isn't?
Yeah, if you know that it's not Gaussian, you might do better with a different objective. And you actually can find, there's lots of distributions where you can kind of go through this similar process and you'll get different objective functions, which is pretty cool. Any other questions? There's this thing called the exponential family. I'd recommend looking that up. Okay. So sometimes it turns out, so we derived this least squares objective. It turns out sometimes we can keep going, because we still need to optimize this. So, a lot of people will optimize it with like gradient descent. A lot of neural networks use this as a function to optimize. But sometimes we could actually keep going and get an analytical solution. I'm not going to show how to do that right now, but if you want extra practice, you can check out example 2.9 in the textbook. It turns out it just requires that this f theta of x is a linear function. So you can check that out in the textbook. It turns out there's also ways to derive analytical solutions for maybe like non-conditional distributions, so standard distributions like a Gaussian distribution, which you can see in example 2.8 of the textbook. And a Bernoulli distribution, which you can see in example 2.7. So if you want extra practice on all these concepts, I would definitely recommend checking out those examples. Yeah.
Wait, what did we just do? assumed data was Gaussian.
Yeah, good question. We assumed we had x, y pairs, so we had an x input and a y output. We were modeling things as a conditional Gaussian distribution. Example 2.8 just shows like if you have a bunch of x's, there's no labels. How do you fit a Gaussian distribution? Yeah, and it's nothing super mind-blowing. You basically find out that the mean of the Gaussian distribution is just the mean of your samples, and the standard deviation is calculated similarly. All right, so that's maximum likelihood parameter learning. So there is another option, and that's Bayesian parameter learning. So I really like Bayesian parameter learning, and let me explain why. So people who know me know that I'm like an insanely indecisive person. Even though I work in a lab that focuses on decision making under uncertainty, if I have to make a decision for myself, it just doesn't work. Bayesian parameter learning is just perfect for indecisive people like me, because why pick just one set of parameters when you could just maintain a distribution over all possible parameters? So that's what we do in Bayesian parameter learning. So we have our parameter theta, and we want to maintain a distribution given our data over what we think those likely values for the parameter theta is. Okay, so what we want to calculate is this p theta given d. So we're saying we have this data set, what is the probability of some particular value of theta? And we don't know how to directly compute this. So just kind of by looking at it, we can't actually just derive an equation for this. But what we do know is how to compute PD given theta. And so we actually did this earlier when we were doing the maximum likelihood parameter learning. So if you remember, we assumed we had this data set of a bunch of different observations, and then we showed that if we assume that they're all independent, we could just compute PD given theta as the product of all of their probabilities given some set of parameters, or some instantiation of our parameters theta. So it turns out using Bayes' rule, we could actually then derive a formula for a distribution of p theta given d. But first, let me just quickly derive Bayes' rule for you. So hopefully many of you have seen it before, but essentially what we're trying to figure out is this p y given x. And we have this definition of conditional probability that I already talked about earlier. So that's one definition. And then all I'm going to do is just rewrite this, switching x and y. So this is still true. Px given y is px and y divided by py. And then all I'm going to do is multiply, so rearrange these a little bit. So I'm just going to multiply the px over here and the py over here. Then you can see we have the same thing on the right side of these equations. So that means we can set the two things on the left side of these equations equal to each other. So I'll do that. And then all I'm going to do is divide both sides by p of x. There we go. And there's Bayes' rule. So it's not super crazy. It literally just comes from the definition of conditional probability. And a lot of times, though, we tend to go one step further because it can be quite difficult to calculate this just plain p of x. And so we often come over here and apply something called the law of total probability to rewrite this p of x in terms of p of x given y and py. Okay, so that's Bayes' rule. And the way that this helps us in our scenario is, you remember we have this p theta given d. And so now we can rewrite it in terms of pd given theta, which we said we actually did know how to calculate. So we have this pd given theta times p theta divided by pd given theta, the sum over all possible values of theta of pd given theta times p theta. So we call this Bayesian parameter estimation. And let's think about this formula a little bit more. So this is what the PD given theta part, that's what we call the likelihood model. So that's what we were optimizing in our maximum likelihood parameter learning. Yeah.
Sorry, when you took this, you did the law of probability, I think maybe the sum is the other variable, but you might also just be misremembering here. So we have this probability of x is equal to the summation over x.
Oh yeah, that should be one.
Okay.
Yeah. Thanks for pointing that out. I'll make that correction before I post these slides. So we have this likelihood model, and then we have this thing we haven't really talked about, which is p of theta. So this is kind of in addition to the things we use for maximum likelihood parameter learning.
Now we have this P of theta, which is a prior distribution over theta. So this gives us kind of what is our prior belief over theta before we observe any of the data. So for example, if I was flipping a coin and someone just handed me a quarter, I have a prior belief over what the probability of that quarter coming up heads is. I think it's probably around 50%. So I'd have some prior distribution that assigns high likelihood to 50%. And then I would observe some flips of that coin, I would see how often it comes up heads, and then that gives me what we call our posterior distribution over theta, which is after we observe the data, what is our distribution over the likelihood of different values of theta. So that's for the discrete case. For the continuous case, essentially the summation at the bottom here just gets replaced by an integral. But there's still one problem here. So we've now transformed it so that we have everything in terms of PD given theta and P theta, which we know how to calculate. But it still can be quite difficult to actually calculate what comes out here. And that's because this summation grows exponentially with the number of parameters that we have. And this integral is often quite difficult to compute analytically. Sometimes it's impossible to compute analytically. And so a lot of times we actually just can't even do this computation. But what's really nice is we can compute this numerator. So it turns out that there's various algorithms that if you can just compute the numerator, you can actually get samples from the posterior distribution that comes out using something called probabilistic programming. I think this is probably a good place to stop for today. So I guess I am going to have to leave you in suspense because I had all these frisbees and we were going to do this really fun thing, but now you're going to have to wait till Tuesday for that. So what questions do you guys have for the remaining few minutes?
Sorry, can you say a little bit about how it's pull from the continuous case when we don't know what?
Yeah, that's what I'm going to leave you in suspense for because that'll be what comes up on Tuesday. The question was if I could say more about how we actually go about drawing samples if we can only compute the numerator.